The sticker should be gravity.
All right, so for our first talk of the morning, we're very happy to have Pavel Putrov from the IAS, and he'll tell us about integrality and analytically continued Chern-Simons.
Thank you for inviting me for this very nice conference. So my talk is based on some part of the work which was done in these three papers with Sergei Gukov, Khovanov-Rozansky, and Dupay. So let me start with the motivation part. So we can see the M3 closed, to be specific, it's oriented three manifold, and as already appeared a few times in this workshop, there exists a certain invariant of three manifolds, which is called w.r.t invariant, or equivalently this is can be realized as a partition function of Chern-Simons theory of the three manifold, and it depends on the choice of Lie group, which I usually throughout my talk I will almost always assume it to be SU2 for simplicity, and I have to fix a choice of positive integer level k. So usually in my talk I will suppress this dependence, and we suppose we're interested in asking the following question. So we know that if you consider w.r.t invariants of links, we know that they can be also realized in terms of Jones polynomials, and there is a categorification of Jones polynomials in terms of Khovanov-Rozansky homology. So we want to ask a question: is there exist a similar categorification of w.r.t invariant? So before asking this question, one should ask a question: is there a sort of relation between these numbers defined for integer levels and analytic function of q's, such that suppose we expand them in q, they have integer coefficients, integer powers of q, suppose maybe up some model shift. If this would be true, then one can hope that we can find the underlying homology. So that similarly to the Khovanov-Rozansky story, we would have a categorification in the following way. So again, in the case of invariance of links in S3, this was a kind of obvious relation. We just have a Jones polynomial here, and we replaced to get a Rashid-Kiev-Turaev invariant. We just need to replace q to 2 pi over k to the corresponding root of unity. So to show that this is there is no simple trivial equality even in some simple for some simple three manifolds, let me give you a very simple example. So let me take M3 to be length space 5,1, which can be realized as a quotient, a specific quotient of S3 modulo Z5. And then there is one can write, in this case, one can actually write the expression of w.r.t invariant as some analytic function of k, and it looks as follows. So here, for simplicity, I took out a common factor. So in this case, all the expression is quite simple. it doesn't have such nice properties. So this relation between w.r.t invariant and functions of Q, which has some integrality property, should be more non-trivial. So physics suggests that there actually should be a solution to this question. And let me make a brief review of physical part of the story. So this story was already extensively used for the case of knots in S3. And now we want to apply basically the same setup for the case of closed three manifolds. So as was mentioned by Kumron on Monday, one can, using the six-dimensional, what is called 2,0 theory of, so in case when my Lie group is ST2, I need to pick the theory of type A1. In general, they are classified by AD. And I want to put it on M3 times disk, which is usually realized as a sort of cigar, times S1, which I interpret as a time direction of my quantum field theory. And then, as Kumron said already on Monday, this setup gives us some homological invariants of three manifold labeled by some choice of A, choice of boundary condition at the end of the disk, which has the meaning of the Hilbert space of the 6D theory if I treat this direction as time. And it has a double grading. Where physically one of the grading corresponds to what is called R charge. And mathematically it corresponds to homological grading. And the second grading physically corresponds to a spin, or equivalently eigenvalue of the rotation generator, which rotates my disk. And here, so when I decompose it with respect to grading, so my homological grading runs over integer, but the spin grading actually runs over integers, plus possibly with some shift, some rational shift, which depends on the choice of boundary condition here. And then, so in this setup, if I calculate the partition function, if I take my time to be indeed S1, so this gives me some six-dimensional manifold with boundary on which I put some boundary condition. I get some quantities which can be realized as traces over the Hilbert spaces and can be written as follows. So here, when I calculate the partition function, I need to interpret Q as some sort of metric parameter in my product of the disk and S1, which tells me how I rotate the disk when I go around S1. But now there is a question how this so this seems to produce us some nice Q series with integer coefficients, but the question is still how it's related to Chern-Simons partition function or w.r.t invariant. And
So the indices, did you write I and J, but I seem to be shifted, but you have J.
sorry, okay, here I think I put it different. Should be I, J. So this thing will belong to delta R. Thanks. So in order to relate this to Chern-Simons theory, I will use a duality chain which was considered by Witten when he wanted to have physical interpretation of Khovanov homology. And so we start with the 6D setup, which is written on the blackboard. And then there is a statement that this setup can be equivalently realized as a. So if I talk about the partition function z hat, it can be realized as a partition function of certain gauge theory, which is usually referred as n equals 4 superrank Mills, is SU2 gauge group. And I need to consider it on a product of M3 times R plus, where at the origin of R plus I put a certain boundary conditions which are called numpole boundary conditions. And here I say that the my gauge field asymptotically approach a flat connection. So from this point of view, the partition function z hat of M3 should, morally speaking, count number of instanton solution on this half line. If I write it in the following form, so this n has a meaning of number of classical solutions with instanton number being I. But this is something which is in principle very hard to calculate and define precisely as well, but might be possible. And then this system in turn can be related to a similar system by what is called S-duality. So in my dual system, I also consider n equals 4 superrank Mills on a half line times M3, where here I put some generalization of Neumann boundary conditions on my gauge fields. And here again I choose a flat connection condition.
You put a prime on the flat connection.
Yes. So this means that the partition function here are not exactly related, but there is a linear transform between them, which
I take all of the flat connections.
yeah, the fact that the partition function here is given by a certain linear combination of partition functions here, which I will explain a little bit more in detail in a moment. So what is so this system already can be related to analytically continued Chern-Simons theory. Namely, the statement is that so first of all, on the physical level, the statement is as follows: that in this setup, the partition function which we calculate, which I will denote by E A prime, So in terms of Chern-Simons, path integral can be realized as follows. So I integrate dA times e to the ik times Chern-Simons functional. But what I do actually, I do my integration in a certain contour, label it by A prime, and this is a half-dimensional contour in the space of SL2C connections divided by gauge transformations, and I take a universal cover of this space. Equivalently, this could be realized by dividing by not all gauge transformations, but only by gauge transformations connected to identity. And this contour is can be described as a Lefschetz symbol associated to critical point A prime. To be precise here, when I talk about flat connections, to be precise, I'm talking about connected components of flat connections. So this is something which still uses, it's not probably not very well defined because it uses some infinite dimensional integrations, but this actually can be given a more precise sense using resurgence. And this is what was developed in this paper with Gukov and Marinho. Namely, one can realize these quantities as certain generalized Borel resummations of perturbative expansions around A prime. So in the case of A prime being trivial, this is what is known, this perturbative expansion is what is known as a Tsuki series, which we mentioned in Anna's talk. And so I don't have time to go into detail, but this is something which can be made quite precise. So the perturbative series, also they are asymptotic, they are divergent, but they can be Borel resummed. So the statement of duality tells us, the S-duality tells us that there should be linear relation between quantities z hat and quantities. Both of them are, so this is some analytic function of Q, and this is some analytic function of K. But let me mention that it's only analytic locally because of the Stokes phenomenon, it can have some wall crossing phenomena. And now, so again, what is the relation to w.r.t invariant? The relation to that we expect. There is a statement that the w.r.t invariant can be expressed exactly as a certain linear combination of these integrals over Lefschetz symbols, because basically we can the w.r.t invariant can be represented as an integral of a certain contour in the space of SL2C connections, and then these contours can be always decomposed into a basis of contours which are given by Lefschetz symbols. So there should exist a linear combination of A primes, which gives me w.r.t invariant in the sense that I have to fix my k to be an integer value. And then, since there should be linear transform between those quantities, we should expect some linear combination of that head. And the point, so from physics, one can make some predictions what exactly this linear combination should be. And in what follows, I will tell you what is the, we'll try to make this statement precise, what exactly this linear combination should be. So this was a motivation part of my talk. Any questions? Yes.
How does this statement depend on k? I mean, is there a different linear combination for every k somehow, or
which statement is this?
the equality between the ZWRT and the thing on the bottom?
So, yeah, this is, I mean, this is a part of the question. How like, what is the nature of these coefficients? How does it depend on k? They shouldn't depend. Yeah, the idea is that they depend very simply on k. Well, let me say that. I mean, they're almost constant.
That's a simple question, but could you summarize again how you go from four-dimensional Young-Mills to Chern-Simons theory? How do you see that?
Here?
Probably, yeah. You say you have for the super Young-Mills, and then you write down path integral for Chern-Simons?
Yeah, I mean, the statement is that the path integral of Young-Mills localizes on the integral of Chern-Simons theory on Lefschetz symbols. This is because so it localizes on classical equations of motion. The classical equations of motion are steepest descent flows with respect to complexified Chern-Simons action.
But this is in this S-dual picture, right?
Yeah, this is this picture. So once we do S-duality, we can lift it to 6D theory.
The flows happen in either picture. In the
Yeah.
For the Neumann boundary condition, you actually get a Chern-Simons action weighing them, which is why Chern-Simons is related to the Neumann version. You get a Chern-Simons action from that Neumann boundary condition.
But also, yeah, it's important that the coupling is different here and here. So here the coupling is k, and here the coupling is 1k. But indeed, the series on half lines there.
So the basic idea is that the instance-on equations are the gradient flow lines for the Chern-Simons function.
Yes.
Classically.
Excuse me, do you mean in this formula that you have finite number of those A prime flat connections? Yeah.
Yes.
So what is the question?
You have finite number of those, or are they isolated?
Well, to be precise, there are finite number of towers of them, because in the here I can consider. So since I consider analytically continued Chern-Simons, so I will have to take universal cover. So each critical point, each connected component is a critical point. Connected component critical point, they lift to an infinite tower, labeled by the absolute value of Chern-Simons action. And
And I guess the main principle.
but the point is that when I reduce it to integer number, they all give the same contribution, so the equivalent.
Up to this action, you have
So-
type number.
So non-trivial information only is there is a finite number of coefficients modulo this equivalence relation.
And the reason why there are finitely many is because there are finitely many components of the moduli space, a flat connection.
Yes, yes,
That's the, so this
Yes.
summing set that you want is that set.
yes.
But only abelian or everything?
Here, everything, yeah. Here you have everything. But the trick is that once, it appears that once you do this linear transform, here you will get only those quantities labeled by abelian guys. But here, I don't make a statement that the only left-shift symbols for abelian contributes. They all contribute. And you can see this explicitly.
But after S transform, it's only
Yeah.
abelian.
And you guys don't understand why that.
Not really.
So for this S3 mod Z5 which you did, what will be the set of A's? Can we try to?
I will tell you in the second part of my talk when I consider these examples. Other question? So this was kind of physics part of the talk. So before making some statement, I need to introduce what is called the linked form. This was already briefly mentioned by Kumaran. So this is a bilinear form on the torsion part of first homology. While it's in rational numbers modulo integers, and it's defined as follows. If I pick two representatives A and B, since they're in torsion, I can find a number n such that n times b is a boundary of certain two chain, and then I say that this is equal to intersection number of A and B prime divided by n. Then one can make the following conjecture, that there exist following decomposition of the w.r.t invariants. So here I take the two quotient. The two quotient is just action by taking element to minus element. So this is not a really group quotient. And then I have S AB the following expression. So here I forgot a factor. Square root of 2ki b1 of m3 minus 1. I take a square root of torsion and I divide by stabilizer of the two coaction of A. And here I have a sum of the elements of Z2. And the trivial part of the statement is that those guys that had, they're of the form delta B is some rational number. And okay, the part of the statement, this is a convergent in the inside of the unit circle at least. And here I take a limit q goes to the corresponding root of unity.
I think about this sum, the set that you're summing over as being the abelian representations of pi 1 of n and
yes, so the space is the same as Holmes of H1 into U1 divided by U2. And this is a subset of Holmes by 1 SU2 divided by SU2, where I map. I take a map where I take my image to the carton, and this Z2 arises as the remnant of the Weil group action.
But you should say connected component.
Yeah, connected components. Because I take only torsion, this means I only take connected component.
Do you have a proposal for what delta B is?
Up to an overall shift, this is the value. So up to some overall shift, this is the value of Chern-Simons action of the corresponding flat connection. And this shift, I think it also can be interpreted as some sort of, I think, I'm not sure, but it's related to something like Cassona invariant.
Particularly, it would apply Simon's conjecture, which says that, you know, all the SU2 representations have rational Chern-Simons, right?
Yeah, but here I take only this is abelian. So for abelian, this is actually given by something like this, and this is rational.
And so, did you get these? So this conjecture is a realization of the formula on the right-hand board. And I mean, did you get the coefficients by calculation, or did you get them by, you know, is there some physical calculation that you did that gave you these coefficients, or did you guess them, or?
It's mostly a guess, but it's a kind of indicated guess because from the point of view of this physics picture, we expect that this S-duality is something like a Fourier transform, has a form of Fourier transform. And this is a form of Fourier transform but apparently it only kind of retransforms on the billionth part. And then you check that you see that in examples, in many examples that this works. Yeah. But I would say that, yeah, there is no derivation. It's mostly a guess.
But also in the statement is that if I somehow manage to isolate set hat B's, then I should be able to retransform back and get the IA primes, which encodes
Yes.
all the perturbation around all the flat
Yes.
SL to C connections. Is that right?
Well, I mean, there might be a problem because there are more guys like this than those guys.
No inverse to that.
Yes, I mean, if there might be, yeah. So yeah, there is no.
No.
At least, I mean, there might be a way to define some set of corresponding quantities which depends on all connections. But apparently you don't, if you want to, and then there would be inverse. But apparently, if you want to relate it to w.r.t invariant, you only need, it turns out you only need these abelian guys. So they don't come up.
Excuse me, do I understand correctly that if you look at the first term, then this should give a decomposition of the Kassan-Walker invariant, which appears at the beginning of the series? Did you compute something with this?
Yes, I think. Well, I don't. I mean, okay. Let me don't answer this. I'm not sure, but yeah, we haven't worked this out. But I mean, we haven't worked out this in detail. But
But you guys get the w.r.t invariance.
yes, yeah. We have a double F. Yeah.
But in Otsuki, you know, for rational homology sphere, that you start with the cardinality of H1, and then something which contains the Kassan-Walker. So if you have a decomposition of the series, you should understand.
But it's different.
I mean, the question is how do you expand those? I mean, yeah. Of course, if I expand the whole thing in one of yes, of course, yeah, I should get in the leading order. I should get a
But that transform is highly not trivial.
yes. Okay.
Sorry, although, so that S matrix looks very similar to things you would find in CFT.
Yes.
Is there some underlying CFT here? With
Well,
operators labeled by flat connections?
I mean, it's roughly speaking something like something quite simple, something like U1 level P and W is W with some.
Yeah, that's sort of.
So P, I mean, if I product of PIs, if my decomposing my torsion into the product of cyclic groups.
Do you know the corresponding linear combination in terms of IAs?
In the case of Seifert fiber at 3 manifolds with 3 exceptional fibers, you know. But that formula is more, we can show it more generically.
Yeah.
But we know this exactly this decomposition in certain
But
cases.
you don't have a general sort of
No.
statement about what that should be.
When you do know it, is it a combination, a sum over just abelian representations, or is it a overall?
All. Well, but also let me point out that this combination depends on the. I mean, it's locally constant, but globally it depends on the choice of the argument of k.
And it comes from the decomposition of the cycle into the generators, right? In terms
Yes.
of that.
So if I fix my k, this, I mean, there is a trick to express it only in terms of abelian, but I have to pick kind of left-shift symbols for different values of argument of k, some sort of combination. So essentially, due to Stokes phenomena, actually all information, once I know left-shift symbols for abelian guys, I know actually all left-shift symbols. Because there is a Stokes phenomena which tells me that if there's some wall crossing phenomena at theta, at some angle theta, and if I know those some integer coefficients, if I know those coefficients, and it happens those coefficients are non-zero when this is a abelian guy, and those are other guys, non-abelian guys. But it's actually 0 if this is non-abelian. So the other way around, it doesn't work. And the Stokes phenomenon can be understood in some topological terms, in terms of some Picard-Lefschetz theory on the space of SL2C connections.
Yeah, maybe the instance on numbers. They count flow lines between flat connections.
No, well, if the critical points would be isolated, then yes, but generically they're not isolated. So it's not exactly true. Okay. So, okay, coming to the question. So how, for example, this works for this example. Example 0, M3 equals L51. So there's only torsion part of H1, and it's given Z5. And when I divide by Z2, this means I only have 3 classes, and those 3 classes correspond to flat connections, and in this case they are only abelian ones. And so in this case, the linking form is just this, model 1. And so, for example, the S matrix is, which appears here, is some 3 by 3 matrix, which you can write explicitly. So it has some algebraic numbers. And in this case, the vector of z heads is very simple. They're just monomials, but in general, of course, this wouldn't be true. There would be a non-trivial series. And so on Monday, Kumran mentioned in this case we have some sort of answer for categorification. So let me remind you. So this categorification can be realized in terms of Poincare series. So that if I take t to -1, I should get z hat a's, and they are given in this case up to some overall factor. Simple. They are given by can be given by the following integral. And they actually non-trivial series in Q and T, not just monomials.
I have a question.
Yes.
In general, this z hat, or on the left-hand side, it seems like you're saying it's a power series in Q, but in this example, it has fractional powers.
Well, they are power series up to overall rational shift.
Maybe it's too early for me.
Yeah, it's
the rational shift here. I mean,
this half and 7/10.
it's
Times 1 or
Yeah, in this case, they're just monomials.
oh, and the rational shift depends on the
Yeah, it depends on
D. Okay, thank you.
So, I mean, is this a general feature for lens spaces that actually this power series is just a monomial, or did you get lucky for L5-1?
For SU2, for L P1, P greater than 1, they're all monomials, yes. But for already, like for S3, you only have one guy, and this is something like 1 minus. I mean, we know that this is something Q minus half.
Can you do S2 cross S1?
S2 cross S1, well, it's kind of a bit a degenerate case, but I mean, in some sense, you can do you can do this, but it's just you just have one guy which is 1, and here you have 1.
And for sigma cross S1, what about that?
Okay, sigma cross S1, it's for high genus is actually degenerate. So, I mean, we have the formula for non-trivial fibration, but they're actually, to be well defined, it's the fibration should be so there's a formula for O minus P over sigma G, but to be well defined, P should be strictly greater than 0. I mean, there is, in some sense, you can take P equals 0, but you have to, I mean, the integral becomes, there's integral formula and it becomes not very well defined. I mean, you can, in a sense, define it, but it also becomes trivial, so you just get some, the most contribution comes from just this factor. Yeah, to be precise, we have only this case. You can write a formal formula.
Where is this integral, the last one, where it comes from?
This comes from physics. This is a calculation of this.
It's related to what you said before somehow. Is it possible to see something?
Well, categorification. So this. So you have the 6D system, and you reduce it on the 3 manifold. You obtain some 3-dimensional theory, and you can calculate its partition function on this disk times S1 using localization techniques. And this is what you get.
The claim is if you put t equals
minus 1.
minus 1, then you get.
Yes.
And where's the A dependence?
Oh, sorry. Thank you. There is, there is important factor. Okay, let me write like this. So I insert some theta function like this, where sum over n's with a shift. Thank you.
Fractional part of Q that you're seeing comes from that.
Yeah, this thing. Exactly. Okay, I have 10 minutes. Let's see. So let me consider quite large examples, which are called plumbed three-manifolds or graph three-manifolds. So they're given by a graph where for each vertex I assign some integer number. And the manifold itself can be realized, for example, by considering a dense surgery on a link which obtained in an obvious way from this graph, just by saying that the combination of unknowns and say corresponding to each vertex, if there is a line edge between two vertices, this means the unknowns are linked, and the numbers means framings. So I consider dense surgery on this link. So let me consider M to be a linking matrix of this link O, and it's given by, so it's a matrix for which indices are vertices of my graph, and it's equal to 1 if a vertex is connected, and it's equal to a framing on diagonal elements and 0 otherwise. And let me, for simplicity, assume that it's negative definite, which is equivalent to saying that my three-manifold is a link of some normal singularity. And this is a singular graph of the resolution graph of this singularity.
So is this the same as making some assumption about the orbifold Euler characteristic of the cyclotribal manifold?
You can always find a negative definite point that fails.
We have to choose an orientation.
Because somehow there, the orbifold Euler, or the Euler characteristic appeared directly, and it gave you problems when it was 0.
Yes.
And sort of that has popped up a lot earlier in analysis of these Chern-Simons events. They behave very differently if the Euler characteristic is 0 or not.
Yeah, I mean, yeah, we do some assumption, but there's still like no proof that it doesn't. It can be made for like a positive part. And from physics point of view, we expect that there should be some. Nice. So, so in this case, one can show this, show the existence of those guys at HUDs, and actually, and show that this relation to the w.r.t invariant and you can actually write explicit formula for that hat B in terms of the plumbing graph data. So suppose L is the number of components of my link. So there is another factor like this, and I take integral of a certain contour, which can be interpreted as a principal value prescription. Around the unit circle. So I have a product over all vertices. So this is my measure. And then I have the following factor. Where degree, deg v means the degree of the vertex. And I multiply this rational function of the z's, or variable z's, to the theta function corresponding to my matrix M, exactly it's minus M, which I can interpret as a bilinear form. So to be precise, it's given by the following formula. So I make a sum over a certain shifted lattice. So this is something which gives you the result for the z-heads, which you can press as some sort of invariants, but it gives you a result in terms of the plumbing graph. And you can ask a question, so, okay, we found some analytic continuation of Chern-Simons theory, which, but we found it in terms of a certain choice of plumbing graph. You have to, so if those are really invariants, you have to check that this invariant under the choice of the graph. So if we take a different graph which gives us homomorphic manifold, it should give the same. A priori, this is not obvious because the formula explicitly depends on the plumbing data, and this is what you can show. So suppose you can think about this z-heads, if you wish, as a definition of those formulas, a definition of z-heads for this particular subclass of 3 manifolds. And you can show the self-consistency. So the quantities as elements of the series are independent, so the invariant under Kirby moves, which relate homomorphic 3 manifolds. So the Kirby moves, they look like this on the graph. Equivalent to A plus B, and there is a move like this. A plus minus 1, minus 1. This will move like this. And there is another move which relates disconnected graphs, but which I'm not going to write.
So some of these graphs you've drawn are negative depth.
Yeah.
That graph has a 0.
Yeah. Okay. The statement is that you can still. So if this is actually graph, which has some representation in terms of negative definite, you can still use this formula to get a sensible result.
This formula also works for the graph that has a 0 in it.
Yeah. Yes. Because it's not. It's a bit a strict condition that this formula. So to write it is in terms of theta function. Okay, I need to assume that this is convergent to have M. To write this as a cell, but actually inside, when you consider this as an inside of this integral, you only need a kind of you need less properties to get a sensible Q series.
Can you explain that equation with a theta function again? So there's a z on the left-hand side, and then x is on the right-hand.
Oh, sorry. I'm sorry.
Okay, and the index I is the index you were calling nu before, is that, or v before, is that right?
Yes.
Yeah.
Okay, my time is up, so I will stop here. Thank you.
Questions?
Maybe I'll go again then. I have another question, but it's really fascinating. These I A primes, is it not right that I to think of them as having exponential terms which decay as e to the, or grow as e to the k times the Chern-Simons of the corresponding component in the SL2C? That could be-
Yes.
Yeah.
Wouldn't that be the sense?
And no, that's the ice. And somehow, how should I then think that when I sum those together to obtain the relation to the sets, somehow these different exponents, which are growing like, like the volume, for example, kind of disappear. Can you explain why that disappears, and you get the expressions that we see for the set hats?
Okay. Okay, the point is that hats, they're related to some linear combination to ABs, and those are not integer coefficients in general. But so when I do this certain in the expression which I had for w.r.t invariant, so I had something like this. And so this gives me so to be okay here. Okay, to be precise, so here there is the overall shift. Okay, what I want, so these coefficients are still has some sort of simple dependence on k, such that the final sum is so my final sum will be of this form. By the simple coefficient, I mean there is something of this form. Okay.
Where delta b could be now, or is it the same delta b's as we saw before?
No, sorry.
Delta b can be complex now.
Yes, it can be complex. But finally, what happens is that, here you get just this expression where these are just locally integer numbers, and these guys are of the form 2 pi I k of Chern-Simons A. So here the sum is all flat connections, all connected components, flat connection. Okay. And if you wish, so those I they have non-perturbative definition, they're not perturbative quantities, but if you wish to expand them, they will have some expansion like this. So they start with some power, and then we'll have expansion of this form, of course, with some coefficients.
So somehow you start with the IBs that they grow exponentially fast, some of them, and then but you were
Well,
saying
in finite sum, I only can I cannot have I only have non-zero coefficients, which those are either real or have positive. I mean, appropriate sign of the imaginary
Yeah.
part.
somehow these CABs, well, you wrote out something else. I mean, so this delta B twiddle is such that it cancels with the exponential growth of IB somehow when you do this next sum.
Yes.
But that could sort of only happen, I suppose, with delta B twiddle is basically the Chern-Simons minus the Chern-Simons.
Yes.
Right. Okay.
So, for example, though if you take this together with S matrix, so this has a form like this. So this is EA, which is abelian, to the plus some sum with some coefficients, with some other coefficients, non-abelian, and there is the overall factor, which is just this.
So what did you write then? E to the minus 2 pi k times what?
Chern-Simons of A.
Okay.
So to cancel this.
Is there a good example that I should think of where this ZB is actually a sort of, an honest power series in Q, and I have to take this limit, and what does taking that limit look like in order to get sort of CWRT at some root of unity? I mean, is there?
Also, yeah, the limit is hard in general. Because
is there some example where?
I mean, yeah, the examples where this the heads are some sort of mock zeta functions, and you can show that the limit is.
Right. Okay. So
But it's
now in these examples,
yeah.
you get these theta functions, and then like.
But yeah, this is kind of it's not trivial, like analysis statement. And I mean, probably, so let me mention, so in case of this, so in particular case of this Poincare homology sphere, so where H1 is trivial, this is example actually was considered by Lawrence Zagier, and they had this some sort of Q series, and those Q series agrees with what we get from the general formula. And there they show, I mean, there they had a non-trivial argument that that when you take Q to a root of unity, you had.
It says sigma 237 instead of sigma 235.
Yes, you can do this. There also works by Hikami. He kind of did it for more general this manifolds with 3 nodes, but he didn't have this kind of S transform which makes you which picks out separates into integer valued series.
You demanded negative definiteness. Is that because do you actually use a singular resolved complex surface to?
No, this is used if I want to write it some sort of in this integral formula, like to make the zeta convergent. I need the.
Basically, the condition you need is that series converges.
Yes. Yeah, but in a sense, I need so for positive degree, I kind of need to some sort of analytically continuous zeta function outside of the unit. Yeah. because changing the orientation should correspond to changing Q to 1 or Q.
All right, let's thank Pavel again for a very nice talk.